Good morning together. Today we will go on in our lecture considering the s-parameters, and we will consider today a special case. We will consider so-called lossless n-ports, and the starting point for our consideration will be the one port we already discussed in lectures before. So here I again sketched the block diagram of a one port. One wave amplitude A1 will enter into the one port, and the wave amplitude B1 will be reflected from the one port. And now we will discuss under what circumstances now this one port will be lossless. So again, we know if I have a look at the one port in transmission line theory, then we have a certain transmission line, and in the plane, in our reference plane, there is connected a certain load impedance, which is normally shows a complex value. And we already discussed that in this case, S11 is given by B1 over A1, which is identical to the reflected wave in this plane with reference to the incident wave. So S11 is equal to the reflection coefficient we already discussed in a lecture before. So if I have a lossless one port, now I must say the input power will be equal to the output power because there are no losses in our one port. And in this case we can start with the equation that the input power, the power which enters into the one port, will be equal to the output power. And from the definition of the s-parameter and the wave amplitudes, we see that under this circumstance, the half of A1 absolute value square will be equal to the half of B1 absolute value square. But according to this definition here, we have that B1 will be equal to, or that the absolute value square of B1 will be equal to the absolute value square of S11 times the absolute value square of A1. And of course, the ones will, or the half will cancel here, and also in the last step we can cancel A1 against A1. And so we see that one condition for the s-parameter to be lossless is that the absolute value square must be 1, which means also that as the absolute value square must be equal to 1, and of course this also means that the reflection coefficient of our load impedance must be 1. And of course we discussed the load, the reflection coefficient also using our Smith chart. So here I sketched a screwed Smith chart, and we know that the Smith chart is given by the mapping of the normalized z-plane onto the r-plane. So now the question arises, where do all the reflection coefficients lie with the absolute value 1? So it has an absolute value of 1, and of course they all rely on the unit circle of our Smith chart. So we have here that I can draw RL, and if we only consider the absolute value of RL, then all s-parameters with an absolute value 1 will lie on the unit circle of our Smith chart. So we now will consider under which circumstances a two-port is lossless. So we first will study here a special case. We will study the case that the wave amplitude A2 is not injected in a two-port. So the A2 is missing here, and only we see that we assume that there exists a wave amplitude A1 which will enter into our two-port, and as a consequence, of course, we will have the wave amplitude B1 and B2. So in our case again, the input power is given by 1/2 absolute value square of A1, while the output power, of course, is given by the sum of the two. This means the output power is given by 1/2 B1 absolute value square plus 1/2 B2 absolute value square. But since A2 is missing, we will get some easy, simple equations for B1 and B2. B1 is only S11 times A1, and B2 is only S21 times A1 again. So if I now again assume that the input power will be equal to the output power, we have that 1/2 absolute value square of A1 must be equal to 1/2 absolute value square B1 plus 1/2 absolute value square of B2. So if we insert these two equations, we end up in this expression here, and of course here we can cancel A1, and of course here will exist then a 1, and we end up in the condition that for a lossless two-port, the absolute value square of S11 plus the absolute value square of S21 must be equal to 1. This I call the first absolute value condition of a two-port. And if there is a first absolute value condition, then we have to discuss also the special other case, and that we will do in the next step. So I now will consider the second case, and in the second case we will assume that A1 is identical to 0. So you see here in the drawing A1 is missing, and only the wave amplitude A2 will enter our two-port. But as a result, we will also have a reflected wave and a transmitted wave. In our case, again, now P in now is given by this phase amplitude. We have 1/2 A absolute value square. The output power remains the same, but the equations for B1 and B2 now become different because only the wave amplitude A2 exists. So we will get B1 is S12 times A2 and B2 is S22 times A2. Again, our condition is that now P in must be P out, and we have 1/2 absolute value square from A2 must now equal the other side of the term. And again, we see here now in all the equation A1 appears, and we can say, oh, this is wrong, of course, here, and we have here a 1. So we end up in this condition that S12 square plus S22 square must be equal to 1, and we call this, or I call this, the second absolute value condition. So in the last step I will now consider the general case, and in general we have the two wave amplitudes A1 and A2 will enter into our two-port, and as a result we will have the reflected wave here at port 1 B1, which comes out of the port 1, and the wave amplitude B2, which comes out of port 2. So now the only what changes is the input power. Of course, our input power will be given by 1/2 absolute value square of A1 plus 1/2 absolute value square of A2. The equation for the output power remains the same, but now we have to account that B1 is given and B2 is given by the whole matrix, S matrix, which makes now things more complicated. So if we start here again with this equation that the input power is equal to the output power, we end up in this equation. Of course, the half will cancel out, and we come to this equation that the absolute value square of A1, and A2 must be equal to the absolute value square of B1 and B2. So this is not very complicated at the first glance, but if I now want to calculate the absolute value square of B1, I have to take B1 times B1 conjugate complex. And now we must insert this equation here in one term, and we must now multiply this with the conjugate complex element. Of course, there then will arise a lot of terms, and then of course we must the same do with B2, the absolute value of B2. Then we have to use this equation. So you see, here we will have a quite lengthy calculation, and this would take a lot of time. So I just give the result now, and the result now is that the parameter S11 times the parameter S11 conjugate complex plus S21 times S22 conjugate complex must be 0. So this is our final result now. We get from the absolute in the general case, and this we call the phase condition. So now we did discuss about the scaling parameters and which constraints a lossless endpoint must fulfill. And one thing was that we found was the absolute value conditions. And for a two-port, for example, we found these two equations. So if a two-port is lossless, the s-parameter must fulfill these two equations. And the question is now, how can we remember these equations? But this is quite easy if I remember this to be the S matrix of a two-port. And you see here, if you have this S11 square plus S21 square is 1, this means we just have to sum up this Coulomb, which says we have here S11 absolute value square plus S21 absolute value square, and this must be equal to 1. And the same will be true here. Here we have also S11 plus S22 absolute value square is 1. So this is just the result. We got this as a result, and now it's quite easy to remember these results. The absolute value, the sum of the absolute value square of the elements of a column must be equal to 1. And of course this we can now extend quite easily to a three-port. So in a three-port we will have 3 columns, and as a result we will have 3 absolute value conditions. This absolute value condition plus this must be 1, and also this Coulomb elements, the absolute value square of this Coulomb elements must be 1. So of course we can very easily extend this to an n-port. Of course then an n-port must fulfill n absolute value conditions. So in the case of the phase conditions, it becomes more or less very complicated, and in the most cases you don't have a practical application for this.